Oh, hello. It's Groundhog Day, so we're at flatMap, and this is the talk on Lambda calculus. I think so. We were discussing what the topic of this talk really is.
Yes, that's a last-minute discussion here, like what the talk is about.
Yeah,
but it's in some sense about Lambda calculus.
Yeah, or co-Lambda calculus or something like that.
Yeah. So we do the thing we usually do. We start with something like this.
So this is the syntax for the Lambda calculus.
Yeah.
So obviously the topic is Lambda calculus then.
Clearly.
So that's good because it feels familiar.
Yeah.
Okay. So what can we say about Lambda calculus then? We have it's quite succinct. It always is.
It usually is. It's usually just like three things.
Yeah.
And you have variables and you have functions, these Lambda abstractions, and you have function applications.
Right, so you introduce a function in the second line there, and then you apply it in the third line. And the first one is just the variable. Yeah.
So that's kind of the syntax. And then we have like this one computation rule, which says that if you have like a function application and the function part is a lambda, then you can replace the argument in the body of the lambda.
Yeah, so you substitute for the x. Yep.
So if you have like lambda x and send in foo, you get foo back because
so that
you
would be
replaced
like
this x with foo.
That would be like the identity function then in Lambda calculus, right?
Yeah.
Yep.
And and then you can make like more complicated expressions, and you can evaluate them all at once. We like to print every intermediate step.
Yeah, so these foo, bar, and quux now, what are those? So just to be clear.
Yeah, so these are kind of free variables that don't really mean anything.
So they're just things?
So you're kind of just seeing how the expression kind of behaves.
Yeah, so but these are now evaluation steps that you're doing, or?
Yeah, so on the first line, we sort of stripped away the lambda a, and then we replaced all the a's. So this a here, we replaced with the foo.
Right.
And on the second line, well, then we
you had no
kind of
bars.
eat the bar.
Or you had no b's.
Replace all the b's with bar. There are no b's. Apply it to quux, replace the c's, and we get some result.
Yeah, but the interpretation now is that for the final line, what is that? So it's you apply foo to quux, or what?
Yeah, so it's kind of the function application of the function application. So,
it reads like
that.
Okay.
This is the argument to this stuff, and this is the argument to this function.
Yeah. And you can apply that as a function because all we have are functions anyway. So
you can sort of usually assume that if you got a thing, it's a function.
Yeah.
And so this is kind of the recap part where we talk about the stuff we always talk about, and we try to do like something a little bit different in like 5 minutes. But for now, it's like, and usually we do numbers.
Okay, so these are now our numbers.
Yeah.
So these are 5 numbers, and you have named them?
I named them L because they have lambdas in them.
Okay.
So that's new. It's totally different talk.
Yeah.
But the idea is that a number is a function that takes 2 arguments, and the arguments must be functions. So it applies the first argument.
Right. It doesn't look particularly like a number, but...
So we'll just define all these numbers because we might need some of them later.
Yep.
So this is 0, so it applies f0 times to x.
Okay.
This is 1, so it applies f1 times to x. This is 2, it applies f2 times to x.
Yeah, so you sort of interpret that as meaning the number or something.
Yeah, so the number kind of is the thing that does something.
Right, and presumably if you applied f 100 times, that would be the number 100 then.
Yeah.
Okay. Cool.
And you know, you can build kind of anything in Lambda calculus, but the simplest thing that seems like kind of real world is numbers. So we usually do like...
Often you like numbers when programming, yes?
Yeah, sometimes you use those. So we're just trying to do the thing we usually do now. So we usually build like a successor function. So it takes a number and it needs to build a new number. And usually we start by doing it the wrong way first. So if we do like L2
Yeah.
I need to press the right keys.
So that's not the number 3.
No, so the successor function should be like,
Yeah.
so it kind of rebuilds the number,
Yeah, okay.
but it just rebuilds the same number, so we want to throw an additional f in there. Then you see we get 3 f's back.
Yeah, so this will be now your successor function, is that right? Is that what you have down there? Yeah.
Yeah, so that's the same function.
So that's...
And we have stuff like plus and multiplication and things. So plus kind of does the same thing. It kind of rebuilds f, b, and then it applies f a times to the result. So you get like a times more f's than you'd get if it was just b.
So you accumulate the f's for both numbers, is that correct?
Yeah.
So you sort of, yeah.
So you get stuff like this. And like everyone's used to this. We all know and love how this works.
Quite convenient that you can sort of use those to build those large numbers.
Yeah.
Yeah.
And this kind of, this is what people came up with like in 1930s.
Yeah.
And then later in 1924, there was like this paper by Schönfinkel.
Yeah, that's quite a mouthful. Is that one sentence? I don't think it fits in a tweet.
Yeah,
this is
and
before
that's
Twitter, right?
kind of our attempt to find like some motivation for what we're going to do.
Yeah.
And it doesn't fit in a tweet, and it doesn't really motivate things. But it's the closest we got.
But there's something said that few and limited and stuff.
Yeah, so it's this thing we kind of like doing is to like, we have this thing and we try to find smaller things that we can build the things from.
Yeah. So you take things apart until
take things apart and see like which things can we eliminate and still build the same thing.
Right.
And if you do that, then you've kind of...
Then you end up in 1924, is that correct?
Something like that. And you do that over and over, and sort of the last small thing, so the very, very last thing you found, you call it a first principle, and then pretend that you build the original thing from first principles.
Yeah.
So that's
until you find a smaller first principle.
Yeah.
Which turns your first principle.
So the later you find it, the first of it is.
Yeah, okay.
Yeah. But what this paper introduces, it introduces currying, I think, which is very nice, so Schönfinkel to name after Haskell Curry.
Yeah, who came after him, yes.
Yeah. And it introduces like, or it tries to eliminate variables.
Yeah, okay.
And we're doing lambda calculus, so we have a bunch of variables.
Yeah, you had those x's that you introduced, and that's quite clever because, as we're told, one of the hard things in computer science is naming, right? So
yeah,
if you get rid of the names, then you sort of solve that problem.
The variables, you kind of need to get rid of the lambdas because the lambdas introduce variables.
You need to lose the lambdas as well?
Yeah, I think so.
It's kind of rough for a talk on lambda calculus, but okay.
Yeah, it's kind of, well, if this thing catches on, then everything we've been doing here for the last years. But the idea is that maybe you can have like a few functions instead and just use those. And they have like a defined behavior and you just combine them in different ways. And you never like introduce your own lambda.
Okay.
So we call those functions combinators. And for now, we'll just say that the combinator is a function with no free variables.
So these are combinators now?
These are combinators.
Okay.
So because this x refers to this thing, it's a bound variable. This a refers to this a, it's a bound variable. This thing just has f's and x in it. But something like this is not a combinator, sort of, by this definition.
Basically, it's bound because you introduce it using some lambda that you can see.
Yeah.
In some sense. Yeah. Okay.
So there's this part, well, everyone's heard about this, so we kind of know what the answer is. So we're going to get to like the sk and I combinators. And
these look okay. Well,
so yeah, we added kind of more syntax to make like combinator things.
Okay. The S looks kind of complex.
The S looks complex. The K and I doesn't look that bad. We'll just define these. So these are kind of well-known combinators that we know that we should be able to use for everything.
Right.
Uh,
So we'll try to express everything we can express in lambda calculus using these. Is that
Yeah.
correct? Okay.
Well, we could have done the slides in the correct order, but we have this syntax for making these combinator-like things.
Is blah also a combinator?
So no blah is a combinator.
Okay.
We're not going to use it as much as like something like k.
Yes, it's less famous than k and
So
s.
we can evaluate these things, and it will.
Yeah, it swaps the order or something like that. Is that correct?
It's not strictly speaking combinator. This seems better.
Yeah, that's right. Yes.
So it should evaluate to like switching the arguments around, and by these kind of simpler rules than we might have introduced in a lambda.
Okay.
And also it doesn't like do an evaluation until it actually has enough arguments, so we won't get to evaluate.
Yeah, so it's waiting
This,
now
yeah.
for the quacks, or
Yeah,
or
so nothing
whatever you
happens
give it?
before we add like.
Okay.
Ooh. So yeah, the idea is we can rewrite everything we've done in terms of this.
How can we use this?
So
Because it's not obvious. Okay, we have these now, but okay.
So I
what?
is the identity function. Everyone kind of knows how that works. It returns the same thing you sent
How
in.
is it the identity function? Because that's
So ix should return x, or should evaluate to
okay.
x. Yeah.
Right.
I think k stands for constant. So you can use k to make a constant function. So you see if you pass in 2 arguments, it returns the first one.
And then just tosses away whatever the one
Yeah,
was?
so
Okay.
you can make like the constant function that always returns 1 by doing k1.
Yeah, because so if you give it now a 7, then that's just going to be dropped.
Yeah, and s is more complicated.
Yeah.
So we're going to try to make do without for now.
Okay.
So we can try to rewrite some expressions. So we have like some simple lambda expressions we can try to rewrite.
I think we can do the first one. That's going to be I, right?
Yeah, I think so. So what we're going to do is we're going to like pass in some dummy arguments and see like, so this is kind of test driven or something, example-based testing.
Yes.
So it's like, this is how it should behave.
Yeah.
And then make like a copy of it and say, yeah, if I replace this with I, does it still behave that way?
Yeah, then
And
it must
does.
be the same thing.
Yeah, you should get the same thing. Like, and since it's only like 3 variables that it shuffles around, then if you get like the same 3 variables in the same order, it should be the same result.
Yeah, okay.
Uh,
This next one is harder, but it's still okay. Well,
We can do like the testing bit.
yeah,
So we should get B back. And so in some sense it seems harder because, well, if it looks like this, it would be really easy because that's the K combinator.
okay. If you
But
say
it
so.
doesn't, which makes it harder. But this part still looks like I.
That looks like I.
So it still behaves the same.
Okay.
And now things are looking easier because this is the function that always returns I.
So you can use your K now?
So we can rewrite it like so. And we get the same
And
result.
Is that what we started with in the first place? Or is that what you get when you...
Yeah.
Yeah, okay. Cool.
And then we have like UWD.
But this is sort of more of the same, isn't it? Because
Yeah, so this
C thing
seems
is
like
the
this is
identity
kind of
function.
pattern we can just apply. So, you know, this should be the same thing.
Yeah.
So it's the function that always returns the function that always returns I.
Yep. And can you just double check again with the...
Sure, yeah.
Okay.
So you got E
Cool.
both of the times.
So this seems very easy to do then.
Yeah, it seems easy until it gets maybe harder.
Okay.
So
Why it's just, it looks quite similar.
it's very similar, and we pass in some stuff,
Yeah.
and we should get W back, which
So you
is
sort of get the
like the
middle one.
key on the keyboard next to E, so it should be really simple.
Yep.
But we can't replace this with I like we used
yeah,
to.
that was sort of our trick,
We
wasn't
can
it?
replace it with K, I guess.
Okay.
Which kind of works, because it's a function that should always return B, right?
Yep.
Uh,
What about the next one?
Next one is more difficult, so we're skipping that. But this can also be replaced with K.
Okay.
And we kind of follow the same rules that we did last time. So it's kind of like, well, nothing in here refers to a.
Right.
So it kind of must be a constant function.
Yeah. Right. But okay. We haven't
gotten rid of every lambda, but like 2/3 is good.
Yeah. This is like the 80-20 principles or something like that.
Yeah. So we kind of.
Is this also difficult now? Is this difficult for the same reason?
It's difficult for like slightly different reasons, I think.
Okay.
In some sense, it's really easy because we can, let's see. Because we can kind of recognize that this doesn't do much.
Yeah.
So we can replace it with identity. But
right, okay.
But to me, it kind of feels like we didn't follow steps or anything. We just wrote it.
You sort of observed the output, is that correct?
Yeah, and sort of, well, it takes 2 arguments and just applies the first argument to the second argument.
You didn't do it in that sort of stepwise way.
But yeah, we didn't like look at these sub-expressions and stuff, which we maybe wanted to do. Okay. But you know, we can leave it like that for now and say that.
Okay.
It's a nice function. And this one is sort of, in some sense, as hard as the last one.
Yeah.
In another sense, a bit harder because it isn't the identity function.
Right, and I don't rightly know what it is, like just by staring at it.
Yeah, so it's like we can't replace this with I or something.
And it's not K either.
None
so
of this
I sort
stuff
of
is
suspect
K.
that we're going to need S. Is that
so kind of
fair to say?
Yeah, we might be running out of stuff to do with K and I here. Yeah. So you know, we tried. We came up with some rules. And I still don't understand why I put this in this slide rather than earlier. But what we're doing is kind of, it's sometimes called abstraction elimination. We're trying to remove the lambda abstractions.
Yeah,
And what we are doing here is we're sort of trying to gradually rewrite expressions and see that they still give the same result.
Yep.
And sort of come up with rules. And
so
what we've seen is that the identity function is I. So if something looks like this, or if something looks like this,
yep.
This in particular, then we can just replace it with an I.
Yep.
If something looks like this, and there is no sort of free occurrence of x in this sub-expression, then it's a constant function, and we can do this k and put the expression in the thing.
Yeah, so what we're sort of lacking is some sort of rule that would introduce an S and solve some problem for us. Probably.
Yeah, so S is probably there for a reason.
Yeah.
The other thing to notice is that in all the sort of translation rules, all the 2 translation rules, we are passing in arguments to the combinators, but we're leaving one out. So we're not passing anything into I here because the argument to I should sort of correspond to this parameter.
Yeah.
The K combinator took 2 arguments, so we passed in one thing, and then the next argument should correspond to this.
Yeah, so it's still waiting for one parameter.
Yeah, so it's still waiting for one parameter, and that should correspond to the lambda we are eliminating.
Yeah. So is that a clue for how we should apply S as well, or?
Yeah, so S takes 3 things, so we should put 2 things into it.
Oh yeah, because then it's just waiting for the last one. Okay.
And we can look at the syntax again. So the application is, so the function application form is kind of the thing that most obviously consists of 2 things.
Yeah.
If you do like...
It looks like the abstraction is composed from 2 things as well.
We kind of say that because it's our excuse to draw like a tree. But as you can see,
so
only the application bit sort of splits it into 2 sub-expressions.
Yeah, that's where it's branching. Is that what you're saying?
Yeah.
Yeah, okay.
So sort of the lambda bit consists of 2 parts, but this isn't another expression. It has to be like the variable name that is introduced.
Yeah, okay. So it's not an arbitrary expression.
Yeah.
Yeah, okay.
So it seems like, well, we need to pass in 2 things. Function applications turn out to be a little bit hard, and they consist of two things.
Yeah, and that's sort of where we ran into problems when we tried to do it by hand.
So what we're going to do is, like, when we get to a function application, then there's a function part and an argument part.
Yeah.
We want to pass those two things into S.
Okay.
And then it should be like waiting for its real argument. And as you can see, this Z then is passed into the function part here and to the argument part here.
Yeah, so we pass
and then the function is applied. So we need to also translate the function part to a new function that can accept that Z.
Okay.
Okay.
All right, so there's some sort of substitution that's going on in...
Yeah, so it's kind of... At least we like to pretend that S stands for substitution.
Right.
So it kind of...
It gives you some intuition at least, yeah.
Sort of guide the value to the right place for us.
Okay, this is one of the hard ones again now, is that correct? Yeah, okay.
So we'll see if we're supposed to get W back. We can do the same thing we did last time. There's no function application here at the moment, but if we replace this with a K like we did last time, then this thing is a function application.
Yeah, so you apply your K to the B.
So now we replace it with an S, and we turn this into a function that accepts the B, and we turn this into a function that accepts the B, and it behaves the same.
Okay, it's not obvious why you did that, but...
Does this make it obvious and get the W back?
It convinces me that it's probably a good idea, but yeah. Okay, so...
I'm also supposed to like duplicate the line before I do it.
Yeah,
let's just get rid of everything.
Yeah, but okay, let's just roll with it that we sort of pass it along. Is that a way of...
So QW, we get the W back.
Yeah.
We can keep the original expression around this time. We can replace this with K.
Yep.
And we still get the W back. And this is a function application. So this is the function part, and this is the argument part.
Right. And then you replace that with a function that accepts your B.
So this is the S, and it takes sort of the function part and the argument part. But I need to turn this into things that should then be able to accept like the W we're sending in.
Okay.
So this was the B argument, and that should be passed into both of those by the S combinator.
Okay, so let's see if that helps.
Yeah,
Does it help?
It helps. It still works. And these things are easier to...
Okay, those are easier because that's an I, yeah.
Yeah, that's the identity function.
What about the other one?
That one always returns K, so it's K.
Yeah,
K.
Okay.
And now there aren't any A's there, so we can just do this right. And we get the W.
You fixed it.
Yeah.
That's great.
So...
Can we do one more?
Yeah, we're skipping this one because it turned out to be the identity function. But we can do like this one. We should get BA back.
Yeah, this is now a function application again, so it's probably an S that you need to...
Yeah, so the innermost thing is a function application. And we're turning this into lambda x, which we can maybe write at once like this. And then it's a lambda x, but it ends up being like a K of F, I guess.
Yeah. Did that work?
I didn't do great. Yeah, I need to we were supposed to eliminate this one.
Oh, yeah.
Yeah.
Right. And that's again, does it give you the same result as what you started with? Because now we don't have the original one again.
I think you're supposed to remind me to keep the original one around. I forget,
so you need to remind me to remind you.
Yeah, I just did. So we're trying to rewrite this thing, right?
Yeah.
We should get BA back.
Okay.
And we get BA back.
Yeah.
Yep. And there's an F around. Now we have a bunch of function applications here.
Well, that's another function application, and the expression looks much worse.
Yeah, so it kind of gets worse as you keep doing this. But you can do the same thing. This is an F.
Right, and you have the F there as well. Okay. And it still gives the same result. So it must have been correct. And
okay.
you're going quite fast.
Yeah.
But okay, so is this another function application then? So you need yet another S for the last one?
Oh, for the last one, it's another function application.
Yeah.
So lambda f this.
These expressions kind of grow fast.
It's really
that's
fast.
That's KK, is correct? Yeah?
Yeah.
Oh yeah, I'm getting it, yeah. Cool.
So while we were looking for motivation, we found this quote in a blog post. I think the blog post is good, but it doesn't suit like what we're doing.
Yeah, because point free is sort of what we're trying in some sense to do, right?
We did not make it more succinct, and it did not aid our understanding.
Yeah.
But it's kind of neat.
Yeah, it's neat.
And
it's not short and it's not terribly understandable.
And it's easy to name the expression after because you can just say that it's called x or something.
Yeah.
Which I think was like the closest thing to motivation we had to get rid of naming issues.
It's kind of similar to beep boop, right?
Yeah. So we end up with these rules, the same ones we start with, and sort of this S thing that an application.
So now we have our third rule. Excellent.
Yeah. So that's kind of what we do. We wrap the function part and argument part in lambdas and apply S to them.
Yeah.
We don't have a ton of time. Right. So we can make these simpler in a couple of ways. The first thing is to recognize this kind of rewrite rules that a function that takes an argument and just applies some other function to that function can be rewritten to like the function you're applying.
Yeah, so because you're just introducing it.
So lambda x f applied to x is the same as f. And this usually comes up during translation.
Yeah.
Beep boop. There we go. So we can sort of do this thing again and try to look for an opportunity. So we did like, I'll remember to remove this this time. This turned into an I, this turned into an KF.
Yep.
And then we did like this thing.
Yep. Oh, there you have it, right?
Yeah.
Because now you can.
So it turns out this is really just K.
Yeah.
And then we put K over here.
So this is at least shorter, right?
So this is shorter. It's still not shorter than the thing we started out with. But we often miss some of the opportunities to use this rule because expressions get large and we don't notice that there's a bunch of stuff going on and then our argument. So if we didn't do this by hand, then maybe it would be even smaller. And you can kind of move on. So yeah, you kind of extend our rule set a bit.
Right, so you have that rule to sort of drop the abstraction.
So like if it's a thing that looks like this kind of thing, and you know the argument part here is the x that is introduced by lambda and it doesn't occur free here. So there's
so you can just use the u directly instead of introducing this function. Yes.
So that makes some expressions a bit shorter. The other thing is that we end up with a bunch of k's everywhere.
I
so you have this thing going on where you're wanting to remove this x, and then you introduce this s.
Yeah.
And then there's no s there. There's no reference to x in this expression.
Yeah.
So there's nothing interesting going on, but you have to like turn it into a function that returns k because it's going to get past sort of this x into it, and it needs to return what it started out as.
Yeah, so you sort of need to plug up your s or something like that with this case. Yeah.
So sometimes in addition to sk and I, we use a couple of extra combinators that we could like define in sk and I since you can build all the things with sk and y.
Yeah.
But
you're trying to make it succinct, right?
We like to when I do this by hand, I like using these two in addition.
Yep.
And they're called B and C. I don't know. My way to remember it is that B comes before C. so it does a thing to the second thing instead.
Yeah.
In the opposite order of what I'd expect.
Yep.
So like this thing only passes the Z into the second argument, and since it's the second, it's B, and since it's the first here, it's C.
Yep.
Yeah.
Well, we'll just roll with it.
So if you introduce this, then in a lot of cases, we don't need to use the S, and we can just use one of these instead. So we can go back to this one.
Yep. So now, presumably, you can use your new combinators.
Presumably.
Yeah.
So this should return BA. It's a so we want to remove
now
this.
you only reference it in the first part.
So
that
we can
would be the
just
C,
do
right?
like this instead. So we're just passing this X into this thing, which should just return the X.
Yeah. And now is this one of those second rule things, or is that one of the unneeded abstraction
Yeah,
things?
so this is kind of, with parentheses, it would look like this.
Yeah, so you can sort of shed the F, if you like.
Yeah, so now the eta rules applies again.
Yep.
And we get like this CI thing. And now it's actually...
This is now actually shorter.
It's actually shorter.
Yes.
I'm not sure, like... Yeah, we bring up this quote again. And it's actually shorter. Does it aid understanding? I'm not sure, but it's interesting.
Your background, I think.
And I think it's like... It's certainly a different way to look at it, and you can sort of look at these things as sort of guiding the argument value into the right place in the expression, which is like nice to think about.
I suppose if you sort of...
And maybe if you think about it a lot, and by accident you understand something along the way.
Yeah.
But I've, like, just like this and with these combinators, maybe you don't understand it better than the original expression. On the other hand, maybe we did a poor job of explaining the original expressions. It didn't like do
it's
much.
Hard to tell, yeah. But it probably changes the way you think, right? So it's a good way to learn another way of expressing the same thing.
Yeah. Yeah, so that's our sort of final rules.
So you have for introducing B and C.
Yeah.
As
So
sort of special cases for yes.
If the parameter only occurs on this side, we use this.
Yeah.
If it's only on that side, we use that.
Yep.
If it's on both sides, we use the S. And it aids understanding.
Yeah.
Can mostly skip this, but there's some details about how, you know.
Like you could in principle express.
We could have written this instead of I.
Yeah.
And then we wouldn't need that letter.
Yes, now you have two letters.
Oh my God, our understanding would be so much aided. But we're kind of sticking to all the combinators, and because they sort of correspond to somewhat how we think about the Lambda expressions to begin with.
Yep. So now we get to the real world stuff, is that correct?
So this is the real world part.
Right, so here we have a line of real world code.
Yeah. You know how you often want to calculate the average of two numbers?
Yep.
That's what we do in the real world. You see, it has a decimal point there, which we would never be able to do in Lambda calculus.
Yeah.
At least we wouldn't. So it's sort of necessarily real world. But now we have all these rules for translating stuff, so we can get rid of the variables. And then we get, like, score cool points with the Haskell people who like
because
point-free
that's sort
style.
of like best practice Haskell these days, right?
Yeah. So we can just sort of rewrite this to something that looks more familiar to us. We want the function before the arguments, like normal people.
Yep.
So something like this.
This is now much more understandable.
So now we can eliminate the x and the y, right?
Yep.
And
how do we do that now?
well, it puts it in the first place. So this is like the function part.
This is a function application now, right?
Yeah.
Yes.
So we're removing this. C, it was the last one, so it puts it in the first part. Lambda, y. No, this is the function part, and this is the argument part.
Yeah.
So we put it in the other part. We're also going to need like parentheses. Haskell is kind of a Lisp, so we need parentheses everywhere.
Yeah.
And then it's like, but now this is the function part, so the eta rule applies. So we can just leave it as plus x, right?
That's quite fast. Yeah. Okay.
Yeah. I also
and
forgot to do the
X-
testing bit, so we're going to mess up, but that's...
Yeah.
So hopefully this behaves the way it used to.
Let's try it.
So A, B...
It looks nice.
Looks good.
So now all we need to do is eliminate
Get
this
rid of the
x.
x.
Okay.
So what's the function part here? It's the C... No, it's this whole thing. So we want to put it in the first part. And because the second part is just a number 2.
Right, okay, yeah.
And then we want to put it in the second part, because the first part is just the C.
Right. I'm sort of following along.
And then we would like to put it, so it's like this part and that part. I'm completely lost now.
I am as well. Yeah. And this is just plus.
And that's just pass.
Yeah.
We might be good. Yeah,
And we're good,
it looks
yes.
kind of the same.
Perfect.
Uh,
Excellent. And this aids understanding.
So the other thing is that Haskell doesn't come with like B and C and stuff.
Yeah.
But let's see, B looked like X, Y, Z. B was the first letter, so we put it in the first part.
Yep.
Let's see. What function is this?
Oh, it's flip. Is that correct?
Yeah, it's
I
correct,
think it
but
is.
it's for C because I got the order wrong again, I think.
Yeah.
So C is the last thing, so C puts it in the first part, right?
Yeah.
So these should be flip. And then the other thing, so X, Y, Z. Something everyone recognizes as composition.
Yep. Excellent.
Again, it's Haskell, so we need to add parentheses.
Yeah.
So, you know,
Yeah.
maybe this works.
Let's try it.
So we'll use a new number. Moo is this thing.
Okay.
Moo 2 and 4.
Oh, yeah, that's
Can test it
certainly
with
helpful.
multiple.
So this is
pretty useful.
this is how you're supposed to write your Haskell these days, yes?
Yeah, that's my understanding. And it's pretty aided by now. So
And yeah, so we got to the real world, which is excellent, and I think we're sort of out of time.
yeah, I think we're at last minute now. So you can use this to write point-free Haskell, which is fine if you don't do Haskell for a living, I guess.
Yeah. Okay.
I think
Thanks.
we're done. Thanks.
You want to answer questions?
Probably not.
It's possible to talk about these things later on if you like.
Yeah, it's probably easier to discuss it in person. Usually the QA session is me not hearing the questions and then answering something else.
I think there was a question. We got.
Is there like an extra flip and an extra compose, like superfluously?
I can't imagine that anything is superfluous in this.
This is quite concise. So.
Everything in this is necessary to me. There could be. And we often, like I said, we often miss some opportunities to use like the eta rewrite rule because expressions get large. And yeah. We have like a sheet here. X lambda y. So what was it? Times plus
that.
x y 2. So I think we came up with roughly what we come up with when I don't do it by hand, but it's my code that calculates it, so it's probably wrong. I don't know.
Yeah.
Yeah.
So we're done?
We're done. Thanks.
Okay, thanks.